All right, so here I'm just going to be going over these learning objectives related really to static electricity. So having charges in a place that create an electric field. So as a student studying physics, studying static electricity, we want to be able to show an understanding of the concept of an electric field, define electric field strength, draw field lines to represent an electric field, calculate the strength of a uniform electric field, calculate the force on a charge in a uniform electric field, and describe how charged particles move in a uniform electric field. All right. Show an understanding of the concept of an electric field. So just like there's, massive objects create gravity fields and that exerts force on masses, charges create electric fields, and in an electric field, a charged particle will feel a force. And we sort of define the strength of the electric field as how many newtons of force are acting on each unit charge. Here you can see here are some pieces of metal that they probably hooked up to a battery or something like that, and can't really see electric fields, they're invisible, but if we can kind of put some particles inside of oil or something like that, then they kind of the charges are deposited onto them and then they become charged and they kind of show us what the field lines look like. So we can see that there's like these field lines in between these plates, and then they kind of go out towards the sort of end here, right? So they kind of look like that. All right, last week we talked about electric field strength. Here's a very formal definition. The electric field strength at a point is the force per unit charge exerted on a stationary positive charge at that point. You see how they've captured the vector nature of this quantity by including positive charge. All right, it's not immediately obvious until we really kind of focus on it. So if I were writing notes down in my journal about this electric field strength, and so here's a good textbook definition. It's like if you had a paper 2 question that said, state what is meant by electric field strength. And you have like a flashcard that you prepared that has this on it. The electric field strength at a point is the force per unit charge. So that's the key idea, force per charge. Like we need to calculate something, we're going to write E equals F over T. And we're going to, solve what we need to, plug in, what we need to in that equation. But if we're trying to earn the marks for a statement of what is meant by electric field strength, you'll likely lose the mark by not including that keyword positive, okay? It's the force per unit charge exerted on a stationary positive charge at that point. Because then the direction of the field is captured, because we say that the rule is an electric field sort of points in the direction that the proton force is sort of feeling. Okay, so the direction that a proton would move, or the direction of the force that a proton is feeling. And a negatively charged thing would feel a force in the opposite direction, right? Because opposites attract there. So that is really key there, that you have somewhere in your sort of definition of electric field strength, you have sort of that it is a vector, and the direction of that vector, the field, is in the direction that a positive charge is sort of feeling the force, or the force exerted on a positive charge. The force per unit charge exerted on a stationary positive charge. So make sure that you've got that key word, that key phrase in there, and then it makes sense. All right, we saw last week drawing field lines sort of with that rule, sort of radial field lines around a positive charge, where if you put a stationary positive charge right here, then the force that it would feel would be away because like charges repel. So a positive charge would repel a test charge, a stationary positive charge, and the field lines point this way. Conversely, if you put a positive charge around with negative charges, the field lines, sort of point down because the positive charge would move that way. And if you put two charges near each other, then their field lines sort of interact like this. And so you still see that like between them, a proton would be pushed away by this charge, or would be pulled towards this one. And so the field lines just sort of connect here and kind of, go out like this, like we saw with the oil and little bits of grain or whatever it is inside of the oil. So you still kind of get like a combination of these radial field lines and then they sort of connect. So when you're drawing field lines, remember that the relative density of the number of lines that you draw is also an indication of the strength of the field. So if you have like two figures and one of them is packed full of field lines, the other one is just has very few, then you're sort of saying, relatively speaking, one with more field lines is stronger. And the direction, obviously, the arrow of the positive charge. So that's important. Those are the key ideas of drawing electric fields. And you'll see paper one questions where it's like, pictures kind of like this, and your answer choices might be like A, B, C, D, like different points around the field. We'll say, at what point would an electron feel, And so just sort of understanding the key ideas, doesn't matter what question they ask, you kind of know, okay, well, things move this way, these are the forces active. Here's another very typical sort of physics example, parallel plate capacitors we mentioned. So if we hook two pieces of metal to like a battery, and then the electrons that are repelled by the negative terminal of the battery sort of will eventually pile up, okay, on one of the plates, and you get a potential difference between them. Okay, so the voltage is the potential difference, and then the distance between the plates also affects the field strength, right? As we bring them closer together, the field gets stronger. Kind of what we were doing with our Van de Graaff generator on Friday. So, field lines between a parallel plate capacitor should make sense that the field points down because a proton would be repelled by the positive plate and attracted to the negative plate. And then those are the two equations that we have for calculating the strength. We sort of worked with both of them: force per charge, voltage per distance. It's typical that, bless you, in the laboratory, these are things that we can kind of measure. Like we put a potential difference on two plates, we sort of measure how far apart they are, so we kind of know the field strength this way. And then we say, well, knowing that, let me put some, what would happen if I put an electron in there? What force would it feel? And we know the charge of an electron or a proton, or 100 electrons or proton, whatever it is, whatever the charges are. So physics, I've mentioned before, not like what is it equal to? What else is it equal to? Because if these two things are equal to each other, then we can sort of think about what's doable in the laboratory. What do we know is sort of theoretically true? That it's equal to this, and now we know the force acting on it. We know F equals ma, laws. And then here's some physics that's beyond the scope of this course over here, if anybody's sort of interested. Sink your teeth into that. Something to look forward to. Again, it's sort of the same idea that we've got an electric field, you've got some charges here, they got exerting forces on each other, but the force really sort of up the field. And again, a little bit of, I don't think we'll see anything that's sort of this bad, in this class. That's something to look forward to for like college level physics there. But so that's not so bad, right? We've got a component here, you see the sine of this angle phi, okay? So usually we use theta, but what if there's like another angle? So you got like, I don't know where the angle theta is, maybe it's this one over here. And so we need another variable for what do we call some other angle in physics that's not theta, well, it's phi. And if you look at my laboratory, you can see that I put phi very close to the ceiling near the posters over there on the wall that is on the east part of the laboratory. That's a high phi. It's so high up on the wall. And previously, before they cleaned my classroom, I had the Greek letter rho, which we've encountered before, rho density. And guess where I placed that? Very, very low on the wall, correct. So I had a low rho and a high phi. And that's the way we decorate the physics lab. Low rho and high phi. And maybe there's more. We'll have to sort of brainstorm it. I need to remake my rho. Phi is hard to get to. Phi is tough. All right. Describe how charged particles move in a uniform electric field. I say, well, it's like massive particles in a uniform gravity field. Same idea. The same physics that we studied with You know, projectiles moving, as charges moving in electric fields, the only difference is sometimes things can move up. When gravity is always down, things can move up in electric field. And this is more of an idea that we'll get to in current electricity. The idea is a potential difference in EMF. Okay. Here's where we saw how a Newton per Coulomb is the same thing as a volt per meter. All right. We saw the base units of each of those. All right. So electric fields, they're forces on charges. And when we build a circuit, we are creating an electric field in the wires. All right. And so we're exerting forces on charges inside of the wires of the circuit so that those charges get pushed, right? Force exert on them, they accelerate, they move, and then energized charges convert that energy, that electrical energy, to other forms of energy that are convenient for us. Right? So we can think about sort of all the appliances that we can plug into a wall and say, well, why is that useful? Why do I enjoy sort of benefit of this technology? How else would I achieve this if it were not for the sort of clever engineers and physicists that figured all this stuff out and invented this stuff? And then we can talk about the double-edged sword of technology. That's a very quick review of the learning objectives. And again, just kind of focus on the language. You know, it's your job as a student to calculate the force on a charge in a uniform electric field. So when you hear that language, you know what the equation is, and then always connect it to sort of prior knowledge. We've already studied the physics of things moving in gravity fields, so charges moving in electric fields, kind of the same thing. All right, so let's go ahead and